Thank you for inviting me.
I think that at this point, you more than anyone else on this planet has invented so many of the ideas behind deep learning. And a lot of people have been calling you the godfather of deep learning. Although it wasn't until we're just chatting a few minutes ago that I realized you think I'm the first one to call you that, which I'm quite happy to have done. But what I want to ask is, many people know you as a legend. I want to ask about your personal story behind the legend. So, how did you get involved in, going way back, how did you get involved in AI and machine learning and neural networks?
So when I was at high school, I had a classmate who was always better than me at everything. He was a brilliant mathematician. And he came into school one day and said, "Did you know the brain uses holograms?" And I guess that was about 1966. And I said, sort of, what's a hologram? And he explained that in a hologram, you can chop off half of it and you still get the whole picture. And that memories in the brain might be distributed over the whole brain. And so I guess he'd read about Lashley's experiments where you chop out bits of a rat's brain and discover it's very hard to find one bit where it stores one particular memory. Um, so that's what first got me interested in how does the brain store memories. And then when I went to university, I started off studying physiology and physics. I think when I was at Cambridge, I was the only undergraduate doing physiology and physics. And then I gave up on that and tried to do philosophy because I thought that might give me more insight. But that seemed to me actually lacking in ways of distinguishing when they said something false. And so then I switched to psychology. Um, and in psychology, they had very, very simple theories. And it seemed to me it was sort of hopelessly inadequate for explaining what the brain was doing. So then I took some time off and became a carpenter.
Oh,
And then I decided I'd try AI. And I went off to Edinburgh to study AI with Longit Higgins. And he had done very nice work on neural networks. And he'd just given up on neural networks and been very impressed by Winograd's thesis. So when I arrived, he thought I was kind of doing this old-fashioned stuff and I ought to start on symbolic AI. And we had a lot of fights about that, but I just kept on doing what I believed in.
and then what?
Um, I eventually got a PhD in AI, and then I couldn't get a job in Britain. Um, but I saw this very nice advertisement for Sloan Fellowships in California, and I managed to get one of those. And I went to California, and everything was different there. So in Britain, neural nets was regarded as kind of silly. And in California, Don Norman and David Rumelhart were very open to ideas about neural nets. It was the first time I'd been somewhere where thinking about how the brain works and thinking about how that might relate to psychology was seen as a very positive thing. And it was a lot of fun there. In particular, collaborating with David Rumelhart was great.
I see, right. So this is when you were at UCSD and you and Ramahat around what 1982 wound up writing, the seminal backprop paper, right? So
Actually, it was more complicated than that. Um,
what happened?
so I think, around early 1982, David Rumelhart and me and Ron Williams, um, between us, developed the backprop algorithm. It was mainly David Rumelhart's idea. We discovered later that many other people had invented it. David Parker had invented it, probably after us, but before we published. Um, Paul Werbos had published it already quite a few years earlier, but nobody had paid it much attention. And there were other people who developed very similar algorithms. It's not clear what's meant by backprop, but using the chain rule to get derivatives was not a novel idea.
Why do you think it was your paper that helped so much the community latch on to backprop? It feels like your paper marked an inflection in the acceptance of this algorithm, whoever accepted it.
So we managed to get a paper into Nature in 1986, and I did quite a lot of political work to get the paper accepted. I figured out that one of the referees was probably going to be Stuart Sutherland, who was a well-known psychologist in Britain. And I went and talked to him for a long time and explained to him exactly what was going on. And he was very impressed by the fact that we showed that backprop could learn representations for words, and you could look at those representations, which were little vectors, and you could understand the meaning of the individual features. So we actually trained it on little triples of words about family trees, like Mary has mother Victoria, and you'd give it the first two words and it would have to predict the last word. And after you trained it, you could see all sorts of features in the representations of the individual words, like the nationality of the person and what generation they were, which branch of the family tree they were in, and so on. That was what made Stuart Sutherland really impressed with it, and I think that was why the paper got accepted.
Very early word embeddings, and you're already seeing features, learned features of semantic meanings emerge from the training algorithm.
Yes, so from a psychologist's point of view, what was interesting was it unified two completely different strands of ideas about what knowledge was like. So there was the old psychologist's view that a concept is just a big bundle of features, and there's lots of evidence for that. And then there was the AI view of the time, which is a far more structuralist view, which was that a concept is how it relates to other concepts. And to capture a concept, you'd have to do something like a graph structure, or maybe a semantic net. And what this backpropagation example showed was you could give it the information that would go into a graph structure, or in this case, a family tree, and it could convert that information into features in such a way that it could then use the features to derive new consistent information, i.e. generalize. But the crucial thing was this to and fro between the graphical representation, or the tree structured representation of the family tree, and a representation of the people as big feature vectors, and the fact that you could, from the graph-like representation, you could get to the feature vectors, and from the feature vectors, you could get more of the graph-like representation.
So this is 1986.
In the early 90s, Bengio showed that you could actually take real data, you could take English text, and apply the same techniques there, and get embeddings for real words from English text. And that impressed people a lot.
I guess recently we've been talking a lot about how fast computers like GPUs and supercomputers is driving deep learning. I didn't realize that back in between 1986 and the early 90s, it sounds like between you and Denjo, there was already the beginnings of this trend.
Yes, there was a huge advance. I mean, in 1986, I was using a Lisp machine which was less than a tenth of a megaflop. And by about 1993 or thereabouts, people were seeing like 10 megaflops. So it was a factor of 100. And that's the point at which it was easy to use because computers were just getting faster.
Over the past several decades, you've invented so many pieces of neural networks and deep learning. I'm actually curious, of all of the things you've invented, which are the ones you're still most excited about today?